Hi, my name is Wajid. I'm presenting this paper. This is Smell Detection Tools, a systematic mapping study on the behalf of all the co-authors. Software testing is a essential part of software development lifecycle. As a part of software development process, developers create and update their system test suite to ensure that the system under the test adheres to the requirements and provide expected output. However, test code, similar to production code, is subject to bad programming practices, smell, which is hamper at the quality and maintainability of the test suite. In 2001, a catalog of test mill has been steadily growing throughout the years. While some test mills focus on traditional test system, researcher has also studied the impact of these test mills on other programming languages and platforms. Problem statement. With the growth of the test-smell studies, recent literature review that presented in these slides has been proposed to study various dimensions related to these antipathogens. These literature reviews has explored the various definitions of the test-smell, empirical analysis of their survivor spread, refactoring, and their relationship with changing and bug poisonous of the source code. However, little is known about the toolsets used to detect this smell. The availability of the tool is vital for software engineering researcher and practitioner. Without a thorough understanding of available tools and how these tools compare to one another, it will be difficult to conduct future research that uses the right toolset for a given research problem. Therefore, our work complement these reviews by not only extracting all these smell detection tools published in peer reviews, venues, but also providing more in-depth detail about them. To facilitate their adoption, or considering we compare and considering multiple attributes of these tools, such as supporting the smell type, targeting environment, detection mechanism, etc. And hence, our work provide a catalog for the developers and researchers to support the adoption of these tools. The goal of this study is to provide developers and researchers with a one-stop resource that can offer comprehensive insight into this smell detection tools. In this research question, we have two main research questions. What the first one, what this smell detection tools are available to the community, and what are the community smell type, what are the common smell type they support. And the second research question, what are the main characteristics of the test smell detection tools? The study design, research, and selection. To determine the optimal set of the search keywords, we conduct a pilot study on two well-known digital libraries, MIM and IEEE. This process intends to identify relevant words or synonym utilized in test smell publication. We perform multiple instances of pilot research, where each instance involves reinforcement of the keyword terms in research query. We conduct our query only on the title and abstract of the publication. We decided to apply the search on the publication metadata instead of the full text to avoid false positive. The final case string, the search string in this study is presenting here. We apply our study in six digital library. So inclusion and exclusion criteria. Inclusion and exclusion criteria are crucial in viewing our search space, reducing bias and retrieving relevant peer-reviewed scientific publication. Selecting publication of these criteria become our starting point for manual filtering to see whether they fit in our study. Propose adopting this small tools. The initial pool of publications also serve as backward snowballing, which analyzing publications cited by the selecting pool, and forward snowballing, which is analyzing publications cited our poll publications. So, and we detail how we process and filtering the publication we obtain from our digital library search. Our initial search of the six digital library resulting in 436 publication. with scientific direct, resulting in the highest number of publications, 126. Next, we employ our four stages quality control process to filtering out publications that were not part of our inclusion criteria. The figure shows that the filtration stages. This quality control process involving three authors manually reviewing the publication to determine if the publication can pass from one stage to another. The first stage starts with the removing, duplicating, and retracted publication. 74 publications were removed, and 372 candidate publications made it to the next stage. In the second stage, we apply our inclusion and exclusion criteria to title and abstract. For instance, we discard all the publications that were not peer review or did not propose or adopt a tool. This through a procedure resulting in only including 54 publication. The third stage is involving full text analysis of each selecting publication. Using our inclusion and exclusion criteria, we retain only 30 publications. In the last stage, we performed the forward and backward snowballing sample, resulting in 17 publications. Therefore, we ended up with the final set of 47 publications. So, as we can see from the bar chart, the first small tool appeared in 2006. Since then, there was steadily trend of one or two tools appearing every 1 or 2 years until 2018. The year 2019 and 2020 witnessed a notable increasing in tool-based publication comparing to the prior years, with approximately 51% of the tool development and adoption publication occurring in these 2 years. There can be many factors influence this recent hype. We have observed the following: the dynamic nature of detection mechanism of traditional state-of-art tools made them a very comparable project with the constraint over how test files can be written and located. Therefore, traditional tools are implementing to run as a standalone application or plug-in in IDE. So, in the second part of the first research question is presenting the timeline of all the releases of the 22 test-smell detection tool. Analyzing the test-smell detection tool by each tool. If we look, there is three colors: the blue, red, and green. The blue one is showing that the number of the new test-smell types, and the red one is showing that the existing test-smell type, and the last one, the green, is showing the total number of the detected test-smell type. So if we read the graph from the left to the right, from the oldest to the newest, and we can see here, for example, the general feature is the one presenting here as a new test-smell. But if we look it for the other tool, its own name is highlighted in the red color, which is not proposed as the new test-smell in this tool. So from this graph, we can see that the highest number of the test-smell, the tool is named testland, and following that JUnit presenting in the first 21 detection test-smell, and the last two and the other tool presenting is TS-Detect presenting in 19 test-smell. So to examine the type of test-smell detecting by the identifying tool in our set, we observe that there are a number of the test-smell associated with more than one name, but with similar description of its symptoms. For example, assertion list test, and unknown test defined as an absence of the expected assert in the test method. Similarly to the duplicated code and test code duplication defined in the same issue of the existing of the code clone. So from this table, we observe that three common test-smell type, which are a general feature, is 9 tools detecting the general feature, and following by eager test, which 7 tools detecting eager test, and assertionless relay is for 6 tools, and so on. So we can see that to identify these tools, we observe that type of the supporting for programming language, specifically Java, Scala, Smalltalk, and C++. From this set, Java is the most popular programming languages for TestSmell support, supporting 39 smell types, following by Smalltalk, 28 smell types, and we also see the publication adoption in our dataset to analyze these type of smell. We review our set of this smell detection tools with respect to the 8 characteristics. The 8 characteristics are listed here. So here we're presenting the main table that listing all the characteristics of the tool. In case we cannot locate it, needed information, we label it as UNK, unknown, in the table. It's evidence from the table that the majority of the test smell detecting tool, approximately 87%, focus on detecting test smell exclusively for Java-based systems, and mostly focused on identifying any aviation from guideline of the JUnit testing framework. This further corresponding of our prior RQ finding, where we show that most smell types are eager toward to Java systems, and thereby most researchers around the test smell focusing on dataset composed of Java system. Additionally, there are 3 types. There are 3 tools named TestQ, TestHood, and TestEvoHood, which are supporting 2 or more testing framework. In terms of the correctness, most of the tools do not publish detail around their accuracy. Additionally, the majority of the tools do not report on the performance speed and execution time of our executing time. Our finding shows that only 6 tools publish their detecting accuracy in terms of precision recall or F measure. From our set of 22 detection tools, only 5 tools provide refactoring support. In terms of the tool availability, we search for the link to the tool website or binary. From these 22 publications, we were able to only locate 17 tools. In terms of the detecting small detection techniques, our analysis shows that while most of the tools in our study rely on the static analysis of the source code, some tools identify smell through the dynamic analysis. This technique strategy can be grouped into 4 categories, named matrix, rule, heuristic, and information retriever, and dynamic tinting. The first is standardization of the smell name and definitions. From our QU, we observed that an overlap of the smell types detecting by the tool. For instance, assertion relay is detecting by 6 JUnit support tools. Second, improving support for non-Java programming languages and test framework. From our RQ2 finding shows that the most of these tools are limited to support Java systems that utilize the JUnit testing framework, therefore narrowing test smell research to Java system. The third, don't reinvent the wheel. Some of the tools in our dataset are based on our other tools in the dataset. For instance, J noise test and riot test are built up onto TS detect, and RATS is built up on taste tool. It's important that when introducing new tools maintainers should design their tools to be ready for customization. The fourth takeaway is improving the transparency on the quality of the tool. As a report in RQ2, only a few tools supporting on the correctness of the tools. Further clarify around the bias immigration is not completely addressing for the tools that do not reporting the correctness score. The last point, expanding from just detecting test smell to interactive refactoring. Granting that primary purpose of these tools is to detect of the test smell, developer will highly benefit from the suggest refactoring template for each smell types. So here for the replicating the packages, so in our study packages and the dataset is available online on this link. Feel free to use it and replicating our study. And for further and more information, please visit our website here. Contain all the information. Here is the summary of the presentation, and I would like to thank you very much for watching this video.